So basically, to give a really short introduction about the speaker today, he's an assistant professor of computer science at Rice University, where he leads a research group on human-centered artificial intelligence. His contributions have featured in highly selective academic venues and in collaboration with industry partners resulted in novel robotic systems. He received his doctorate in autonomous systems from MIT. Before joining Rice, he worked as a researcher at X, the Moonshot Factory, which was formerly Google X. So now I'll hand it over to Vaibhav.
Thank you, Ivy, for the introductions, and thanks to all of you for joining in. I'm really excited to be virtually visiting all of you and sharing a little bit about what I do in my research, what I do at Rice, and especially discussing what I think about robots that work with humans. So this talk or this meeting, it's I'm happy to make it interactive. So if you have any questions at any point or even any comments at any point, feel free to jump in. All right. So as Connie said, I'm a computer scientist working at Rice University, and I work in the area of AI and robotics. So I look at robotics from a standpoint of artificial intelligence. So I look at how to design software and algorithms for robots so that they can work well with humans. And in robotics, there is this interesting trend that has been happening over the last 10 years, where we have been thinking about not only robots that can work as tools, but robots that can actually work with us as teammates. So today's talk is going to be primarily about robots such as these, so robots that can be our teammates. So let's look at an example of one such robot. So this is a robot that is working in an automotive factory. So this is a robot that is helping humans who primarily do the assembly of many cars. It's helping them build cars. And there are a lot of exciting things happening in this video. So first of all, there are fancy cars being built. And if you go to a factory, you will see that a car is being built every 2 to 3 minutes. So every 2 to 3 minutes, a new BMW, this is from a BMW factory, a new car is being shipped out. And there are a lot of humans who are helping assemble this car. So that there are really, it's a very challenging process, very time-intensive process. And it has to be done precisely in a very short amount of time. Now, in order to do this task better, and in order to help humans do this task faster, there are a lot of applications of robots that can go and assist humans in making these challenging tasks possible. And this is one of such robots that makes this challenging task possible, called Rob at Work. So this, what I find really exciting about this robot is, as compared to traditional robots, which we'll see soon, this robot can autonomously decide how to help humans, how to work alongside humans using the sensors and software that it has on board. Now, just to contrast it with robots that are primarily in the factories today, or primarily that you would see being sold by companies around a few years ago, would be robots like these. So these robots are also very impressive. They can do very exciting things, very exciting tasks, but they are limited to a very static and caged environment. So in this picture, as compared to the previous GIF, you will see that there are no humans around. So the robots are working by themselves. They have other robots around, but they are working without humans. And in fact, what happens in these for these robots is if a human comes within their cages, the robots have to shut down for safety reasons. So these robots, although very impressive, cannot really work well with and around humans. And that's sort of the challenge that we're trying to solve. And when I sort of look at these bulky, big robots that can do impressive things, I kind of remember, or I kind of think about computers that were present in the 60s and the 70s. So I was not around when these computers were present, but if you talk to someone who has seen these computers, or if you see documentaries from 60s and 70s about the early stages of computers, you would have computers which were so big that they would occupy a whole room or maybe even multiple rooms at times. And these bulky robots that we saw, this big industrial robots that we saw, even though impressive, similar to these computers, are analogous to these robots. Whereas if you look at computers today, they are small, or computers in the 80s, they were small, people could use them and we could program them to do different types of tasks. So robots are also at a very interesting inflection point where they're moving from this industrial settings to settings which are currently industrial, but will soon be in our homes, in our offices. and be able to do very interesting tasks similar to how computers were able to do from changing from 70s to 80s. And this trend of robots moving from safety cages to working alongside humans informs a lot of work that I do and a lot of work that is happening in designing robots that can work with and alongside humans. So let's look at a very exciting example of such a robot. So this is a robot called PR2, which was made by a company called Below Garage. And this company, this robot is doing a very interesting task, very challenging task from a robotic standpoint, while working in a space which is shared with humans. So it is picking items from a refrigerator, and then after picking these items, it decides, it closes the refrigerator and it goes and delivers these objects. So all of these tasks are being done by this robots autonomously again. And it's very impressive that robots are at a stage where they can do all of these tasks by themselves. And this sort of examples that we saw in the industry and in that kitchen are trends that we can see all across the industry. So collaborative robots are one of the primary novelty in the robots that are being sold today, and they are contributing to the exciting growth that robots are seeing in the market as well. And the collaborative robotics sector, so the robots that can work with and alongside humans, are expected to increase roughly tenfold, reaching from around 100 millions to $1 billion of a market within a very short period of few years. So the robot that we saw, which was delivering beverages, like it was from 10 years ago. So it's still a very impressive robot, but it's slightly dated. And this is a very recent robot called Stretch, which was released last year, which is doing even more impressive tasks within 10 years. So let's look at what it can do. So it can do a very impressive set of tasks. And even though it is being doing these tasks by teleoperation, that is, a human is behind and controlling this robot, it's amazing like what robots are capable of doing, even with human intervention today. So like in the past, like when we look at similar to the history of computers, when we look at a history of robots, we had robots like the industrial robots that we saw initially, which have been present for the last 20 or 30 years. And now we have robots such as the PR2 robot, the robot that we saw on the first slide, and the Stretch robot, which are really transforming what robots can do and what is possible with the robots. And what's amazing with this progress is they are also becoming very affordable. So the PR2 robot that was released around 10 years ago was close to $500,000, whereas the robots from today you can purchase at a fraction of cost what it used to cost 10 years ago. So this is a really exciting phase, and sort of gives me hope that I will have robots in my home in the next 10 or so years, which would be able to do some of the interesting tasks that we saw in the videos before. And like in my like education and in my career, I've been really I've been really fortunate to work with some of these robots hands-on, and initially in India, then in Boston, and finally at Rice, where I've been able to like get a sense of how these robots are programmed, how these robots get to sort of reason about the world. And in today's talk, we'll be looking at specifically like what sort of AI technologies are making these robots possible. So after this brief preview, we'll start with the introduction to robotics. We'll look at sort of at a high level how we look at these robots, how we actually program this robot, what sort of programming languages we use, and what sort of challenges we need to solve. Then we'll take a slightly deeper dive into human-robot collaboration. That is, how do we go from a robot that can work by itself to a robot that can collaborate with humans, that can be a human teammate. And finally, we'll look at some of the interesting problems that we are working on today and that maybe you will work on very soon. So let's get started with our introduction to robotics. So we've seen a lot of very interesting videos of robots, and I'm sure you have seen many of these impressive videos or similar robots before. But in order to sort of make our discussion more formal, let's discuss like what do we mean by a robot? So what is a robot? So there are many definitions that you can find for a robot. So this is one definition that I picked from the National Science Foundation. So a robot is any intelligence that is embodied. So it has AI, it has a physical body, which is able to sense, process information, and substantially alter its working environment. So this is a very in a way textbook definition of a robot. So it has to have some intelligence, a physical body, and three key systems: one for sensing, one for processing information, and one for actually physically altering its environment. So let's look at what these systems, and what these modules look like. And here we'll look at this abstract cartoon robot, which has all of these modules. So first, in order to work in an environment, the robot needs to know what is in the environment. It needs to sense the environment so that it can reason about the environment and make changes to it. And to do that, it uses a set of hardware as well as software. So for instance, in the robots that we saw, both in the cage setting and in the human setting, the robots have sensors to know where they are. So these are typically encoders or encoders on their motors, which let the robots know how much they have moved or where they are in the environment. Then, in order to sense what's around them, they usually use cameras or laser scanners. For instance, the robot that we saw in the first slide, which was working alongside humans, has laser scanners and cameras on its base so that it can see what is around it. And in a way, like if you've seen autonomous vehicles, these sensors are very similar to what autonomous vehicles use. So the robots are using these sensors and collecting data from these sensors and then using algorithms to identify what is around them and also figure out where they are. So some of the algorithms that these robots used are called mapping, localization, computer vision, and so on. Then, in addition to sensing, it needs hardware for acting. A robot needs hardware to actually move and actually make changes to its environments. This set of hardware is called actuators. And depending on the robot, depending on the application, this might be very, very different. So if you think about, again, like an autonomous vehicle as a robot, it will have wheels as its actuators. In the robots that we have seen before, they'll have motors, grippers, arms, and so on. And here again, like having the hardware alone is insufficient. The robots needs intelligent algorithms that can reason quickly and efficiently about the information that sensors provide to complete the physical task, to complete the actuation. And finally, the robot needs additional reasoning capabilities, which are which is where the primary AI of the robot resides. And here, this is being sometimes computed on device, so on the robot, sometimes off the robot, and sometimes even on cloud to solve challenging algorithmic problems such as optimization, deciding what tasks to do, how to execute a motion, do reinforcement learning and planning, and so on. So this is sort of the brain of the robot, which allows the robot to reason using the information that it has acquired from sensors and to convert it into information that it can send it to its hardware to actually physically change its world. So in summary, like a robot is a physical entity with sensing hardware, actuation hardware, and algorithms AI to reason and convert sensing data to information for the actuators. And in this robot, as we've been seeing in the example, there are sensors here, if you can see my mouse pointer. So this is a laser scanner, which allows the robot to see if there is a human or any obstacle around it. It has cameras, which also help it do that. And then it has this arm, this wheels, so that it can move around and make changes to its environment. Oh, sorry. All right. So now that we have seen like what an abstract robot looks like, let's look at how do we actually go about programming this robot. So both the robot that we saw, all the three GIFs that we have seen so far, the robot that was working in the factory, the robot that was delivering things from the fridge, and the robot that was being teleoperated, all of them use this exciting piece of software called robot operating system. And this is, I would say, is one of the very exciting developments in robotics in the last 10 years, which has made robotics more open source and more easy to program and easy to prototype. So robot operating system, similar to other open source libraries, is a meta operating system for robots. So it's sort of an app store for robots where you can upload some programs or you can download some programs from other researchers and other users to be useful for your robots. So it has this very exciting features that allows the software use. And it is very important, like it's very important to stress the sort of utility of this feature. So 10 years ago, if you were working on a robot, or if you're working in, if you're designing a robot today from scratch, you might have to develop a lot of capabilities. So you might want to first of all decide which sensors to use, which actuators to use, and then how to implement the different algorithms that the robot needs. What ROS makes possible is if you use ROS, you can use algorithms that other researchers have made and other users have made in your robot. So it sort of really helps you rapidly prototype your system and focus on the elements of the system that you want to focus on. At a high level, it includes certain programs. So these are like computer programs, which are called nodes, and certain messages, which are called topics. And these nodes and topics combine to give robots the autonomy, the AI that it needs to work in its environment. So let's see a very simple example of how we can take a robot and give it navigation capabilities. And we'll take a very simple example where we have this robot working in this map, and the robot has to go from point A to point B. So the robot has to start from here and maybe end up at the top right corner of the map. So to do this task, the robot needs actually a lot of different algorithms. First of all, it needs to know where it is in the map so that it can decide where it goes next. Then once it decides where it is, it needs algorithms to decide what is the best action to take when it is at a particular time. So if it is at the bottom, maybe it has to go up, so it should move up and so on. And then if it sees an obstacle or if it sees something around, it should be able to navigate around them so that it doesn't cause a collision. So it needs really a lot of challenging algorithms to make this simple task happen. And ROS allows us to do that by breaking down this problem into multiple pieces. So first, let's say to implement this task, we might want to use certain sensors. So let's say we use cameras. So ROS will provide us, ROS will require us to write a node, or write a program which takes data from cameras and converts it into, and read that data on our computer. So it will first be asked to write this node. And then we'll also, if we have some additional sensors such as encoders, which tell the robot how much its motor has moved or how much its wheels have moved, it will write that program as well. Once we have this data from these sensors, which are images and now wheel velocity, we can combine these data in a localization algorithm to identify where the robot is at a particular point in time. Then we can use this robot position with planning algorithms to figure out robot's path. And finally, we can give this path to a controller algorithm to decide how should the robot's wheels move. And then this will be pushed to the robot so that the robot can actually move in the map. And if you see like this design of the robotic system, it seems very intuitive when we see the whole system broken down. It has some sensing capabilities in terms of cameras and encoders, which are then combined into localization, planning, and control in its reasoning module. And then finally, these are fed to the hardware, to the actuation hardware, so that the robot can actually move. And what ROS allows us to do is it allows us to actually break down the problem and implement it in a piece-by-piece fashion. So that's sort of one of the first advantages of using ROS. And it's very, so this example, even though it's very simple, it's very similar to how we researchers or programmers of robotic systems who use ROS program robots today. So they will break down the problems into multiple modules and then implement each of these modules to implement their robot, so to design their robot. Now, one might think that if you have multiple robots and all of them use cameras, maybe it's a good idea to write a common camera driver node, which many robots can use. And let's say if you have someone who is working on motion planning, part of motion planning of robots, they can decide a general purpose program which can be used by multiple robots. So that's an additional feature that ROS allows. So you can, let's say if you are using a particular type of camera which others have used, you can borrow the camera drivers from ROS, which somebody else has written, so that you can accelerate your robot design process. Similarly, if somebody has written a motion planning technique already, you can use their implementation to solve this part of the robot design process. And this really accelerates how you can prototype the robot, how you can design the robot, and lets you focus on the element of robot design that you want to focus on. So let's say you are very interested in improving how the robot localizes itself. So in that case, you will use everything else from an existing system, and you can focus on the localization aspect. So ROS and in general robot design, like there are multiple steps involved before we actually have a system that works with people and that works in the real world. So first, when we are implementing a robotic system like the one that we saw on the first slide, we'll start with evaluating the robot in simulation. So we will create a simulation environment, which is similar to a computer game, where we'll have a robot that is working in this environment. And then the robot will test whether the algorithms that we have designed actually work well in the setting. So when I was working on the mobile robot that had to work in the factory, I first designed my algorithms and tested whether they would work in a simpler setting in a simulation. And when I was confident that the system did work in simulation, then I tried doing some tests in my lab. So this is a simple version of the factory that we created in the lab. And then we tested how the robot works within this controlled setting. And finally, when we were confident that the robot works both in simulation and in the controlled lab setting, only then we were able to, were confident enough to move the robot to a real working environment in a factory. And again, in all of these systems, from simulation to the lab to the factory, we were using ROS so that we could use the software that we had used in one setting and reproduce and reuse it in another setting. So that's sort of the design to deployment life cycle for a robot. So at this point, I'll sort of stop for any questions and see if there are any comments that you guys might have.
I have one question. What exactly is localization again?
So localization, thanks for that question. So I cannot see who asked me the question, but localization basically is a module that robots use to localize themselves, to identify where they are in a particular environment. So for instance, here, localization technique would allow the robot to say what its position is given the information from the sensors. Did that answer your question?
Yeah, I have a follow-up. So in this diagram, you mentioned camera drivers and encoder drivers.
Yeah.
So what exactly does the encoder driver do again? And like what do you mean by like the arrow, the wheel velocity?
Yeah. So these robots have a sensor called encoder, which essentially measures how much their motors have moved. So for the navigation example, you might have encoders on the robot's wheels, which will be able to tell you how much the wheel has moved or what's the wheel's velocity. And when you are actually implementing this on a physical system, you need some piece of software to read the data from the motors and convert it into a variable that your localization algorithm or some other algorithm might be able to use. And this transformation from data available from the sensor to a variable that your code can read is what is being done by these drivers. Yeah.
Okay, I see. Thank you.
Thanks for those questions. So yeah, I think what I want to highlight from this sort of this set of examples is when we are programming robots, each of these nodes are essentially computer programs, and we write them in C++ or Python. And when they work, when they are integrated together, in this case using ROS, they help us achieve the overall robotic system. Right. All right, so far we have gone through an introduction to robotics, and we've seen design for a general purpose robot. So a robot that doesn't necessarily have to work with or around humans. So now let's switch gears and look at particularly robots that can work with humans. So that's sort of the main focus of our talk. And the background that we've learned about ROS and learned about how robots are defined will help us also in designing robots that can work with and around humans. So at a broad level, we want, when we are designing robots that can work with or around humans, we want to sort of switch our perspective. We want the robots to not only be tools, which can be used used by a human or a particular human, but we want our robots to be autonomous. We want our robots to be similar to other teammates that we might have when we are working on a task. And in order to design robots such as these, we need a particular set of like requirements to be fulfilled. So first of all, any robot or any system that has to work with humans has to be safe, and that's the preliminary requirement before we can use the robot. But in addition to being safe, we also need certain additional features. So first of all, it would be really nice if our robot is easy to program. So one of the reasons why computers became so popular and we use them every day is because they're easy to program. We can make them do different tasks. We can do different tasks using them. Similar to that, if we want our robots to be really versatile and really functional, the robots should also be easy to program. So that's another very important problem that researchers in human robot collaboration work on. And then in addition to being easy to program, they should be easy to work with. And this is something that we kind of have in computers, but not exactly as to the extent that we have in robots. So we want our robots to be adaptive. We want our robots to be able to identify what humans need in a particular situation and maybe modify according to the human's needs if things change. And that's sort of one of the additional feature that we need. And finally, if you're working with a robot and we cannot understand what it is doing, that may not be ideal either. So we want our robot also to be easy to understand. And when we design robots that are actually human, that actually can be teammates for us, we need to bake in all of these characteristics. And we will see how we can use AI at a very high level to sort of bake in some of these characteristics. So again, let's take a step back and look at why do we need a new set of techniques, a new set of algorithms when we are thinking about robots that can work with humans. And this is to sort of demonstrate this point, I'll show a blooper video from a very famous robot which is trying to deliver an object to this human. And this robot is very impressive. You might have seen videos of this on YouTube or and other places. It can do backflips and like a lot of exciting things. And here it is doing a very sort of, from a human standpoint, a very simple task. It is just handing over an object. But let's look at what happens when the robot actually tries to do that. So here, as you saw, like the robot was able to deliver the object, but it was not very ideal. So the handover, when the object was being delivered, the robot wasn't able to recognize whether the human had picked it up, and then eventually, it just failed. And this was sort of a comical way to demonstrate that it's not as easy to convert robots that work well by themselves and make them into human teammates, because they have to reason about a lot of new challenges when they are working about humans, particularly about like what humans want and like how humans are acting in order to complete the task. And when we are sort of thinking about designing robots that can work with humans, we have to sort of fundamentally adapt our perspective from the perspective that we were taking before, where the robot had this high level perspective of having some observations and actions. And now we need to explicitly think about the human that the robot is working with. So we need to, the robot needs to have particular set of AI tools and models to think about the human, to think about what the human might want in a particular situation, what the human is doing in a particular situation, in order to be a good teammate for the human. And that's essentially like what the research that my group does and other human robot collaboration researchers do focuses on when we are designing robots that can work with humans. So we'll initially look at some of these problems from a high level perspective of AI, and then we'll look at some videos of making these technologies possible. So when we are designing a robot teammate, we need these additional reasoning capabilities to reason about the robot's to reason about other humans and robots environment, and to identify how the robot should adapt, how the robot should move, act, or do tasks around humans. And to do that, we can essentially write a program. So we can write a program which tells the robot what to do in a particular situation. So for example, if we know what sort of challenges or what sort of situations the robot is going to encounter, we can tell the robot, if you encounter these situations, if you see this through your sensors, then do that. And we can write an if-else type program to help the robot, to provide the robot its reasoning capabilities. And this is sort of a solution that we'll call handcrafted policy, where either you or some programmer who's designing the robot would handcraft what the robot should do in each situation. This is a very sort of simplistic way of creating robot teammates, where you're telling the robot what to do in each setting. It requires a lot of programming effort because you have to tell the robot for every possible observation what it should do. But the good thing about this sort of solution is it doesn't require any data. If you have enough time and if you can anticipate every situation that the robot might encounter, you can tell the robot how to act. Obviously, this may not be possible every time, and often in the real world, it's not. So you cannot use this solution to create the robots policy. And here I'll be using this word called policy a couple of times in this rest of the presentation. Here, policy is a word to define what the robot should do in a given situation. So it tells the robot, it's a program or it's a mathematical function which tells the robot what you should do in a given situation, and what you should given some information from your sensors, what you should do in that given situation. So one high-level solution that we can use is writing a program and telling the robot what to do. And this is like an easy solution to start with. And actually, I've used it, and many people use it when they're starting to design their robots. But if you really want to scale up your system to real world, this may not be viable. Another sort of techniques that we use in order to design the AI for the robot, design the policy for the robot, is to use ideas from machine learning. So technique that you might have heard of is called reinforcement learning. And in reinforcement learning, what the robot does is it tries again and again. It tries different options different options, and by trial and error figures out how to do a particular task. So it will do a task once, see if it succeeds or not. If it succeeds, then it might learn how to do that task. If it fails, it might learn how not to do that task, and then repeat until it succeeds to learn how to do the task completely. And this idea, this high-level idea is called reinforcement learning. But as you might see, because the robot is learning how to do the task by trial and error, it might require a large amount of data, even though it might require less manual effort. So here in this sort of paradigm, the robot can actually learn how to do the task by itself, provided it can do many trials. But to learn a very complicated task, a real-world task, it might require a lot of trials, a lot of data. And also, when we are working with robots that have to work with humans, this might also lead to some unsafe trials, which we really don't want when we are designing, when we are fielding a robot next to humans. So there are approaches that we saw first, which are completely manual, where we are creating a program manually. And then there are approaches like reinforcement learning, which are completely based on learning, where the robot is learning its program, learning its policy only from data. And both of these approaches are currently have limitations. In designing robots that can work with humans, we use something of a hybrid approach, where we provide a part of the program, some structure of the robot's program, and ask it to learn some of the parameters from data or from algorithms. So, for instance, this paradigm is called model specification plus planning. So we will tell the robot what is your objective, what is the environment's model, and then it will use some optimization algorithms or even some machine learning algorithms to figure out how to do its task. This also has its own challenges, but because it is safe and it can scale up to larger problems than manual effort, we in my group and also in designing robots that can work with humans, this is sort of the common paradigm that is being used today. But this is a very active area of research, and there are many different solutions to be found in this landscape. Particularly, it would be very interesting to find a solution which requires very little programming and very little data to create general purpose robot teammates. One sort of taking these looking at this challenge of designing the robot policy, of designing the robot behavior from a data standpoint and from a computational standpoint. I also wanted to highlight what are some of the challenges that come across, and this is sort of very specific to using data to train robots, and these are some of the challenges that we are actively working on. So here, when we are training the robot only from data, it's very difficult to tell the robot what is the right thing to do. So this is the problem of robot specification. And here, there might be multiple ways the robot can do a task, one which might be more valid than the others. And it's challenging to specify what is right and what is wrong when we are designing robots. And this is a common problem when we are designing robots, in addition to guaranteeing safe exploration and data collection. So to address these challenges, one sort of set of techniques that my group currently looks at is to use this idea of human-guided machine learning, where we are using data as well as expertise from users and human developers to create our robot. So here we not only use data, but also use knowledge that humans might have to generate the robot policy. And this is up and coming area within machine learning, where we use data as well as human knowledge to improve the performance of a learned machine learning algorithm. So far we have seen at a high level, like what sort of techniques we use and what sort of high level ideas we use. And I'll be happy to take some questions on what these high level ideas mean if you're interested. But before we get to questions, I just wanted to show you some of the different types of tasks that these algorithms make possible. So this is a robotic system that I worked on during my PhD at MIT, where we were designing a robot that can help humans do assembly tasks that can help humans do assembly tasks. And as an example of an assembly task, we had humans build sandwiches using toys, and the robot was delivering them the appropriate ingredient while making these sandwiches. So here the robot had to identify which sandwich the human would make next, where they would make it, and when they would make it to provide the appropriate ingredient. And here the robot has to do a lot of challenging algorithmic problems to complete this task. So first of all, it has to identify where the human is. So it needs certain sensing algorithms to identify where the human is. Then it needs to find out where the human would go next. So it needs machine learning to identify, to predict what the human will do next. And then finally, it needs to use planning algorithms or optimization algorithms to go to that location so that it can give the human correct ingredient. And all of this has to be done very quickly, because if the robot is even a fraction of a second late, the human might go to the next sandwich or might go to the next task, and the robot's effort will not be useful anymore. So all of this is being done by a combination of the algorithms that we saw before. So it is using sensing to identify the humans. The human is wearing a particular glove to make the sensing easier in this scenario, but so that's where the sensing is happening. The robot has a computer on board, which is solving the optimization problem to identify where the human is going next and what the robot should do next. And finally, using its hardware, using its gripper and motors, the robot is delivering those parts. We can also use, when we are working with humans, we can also use communication as a very important tool to do tasks well with robots. And this is, again, like using some of the AI techniques that we saw at a high level. The robot is communicating with the human when they are doing the similar task. So at times it tells the human what they should do next so that it can support them well. And at times it will tell the human what they should, what the robot is going to do next so that the humans can adapt while doing the task. And finally, we have used some of the algorithms that we talked about to do tasks in the factory. So similar, so here the robot is actually not helping the humans make sandwiches, but helping them with assembling different parts in a factory by delivering them appropriate parts or giving them way when they are when they are sharing space with each other. So here again, the robot uses its algorithms to identify where the human is, to predict what the human is going to do next, and then modify its own behavior so that it can adapt to what the human is doing. by using the algorithms that we have developed, the robot can actually be not only safe, but it can also improve the task performance of the human robot team. So that was very exciting, that this robot was both safe and was able to help the team do the task faster. And so I'll conclude this section by saying that there are the collaborative robots that work with and humans are really growing. They are growing in a lot of domains, a lot of applications. So far, we saw a couple of videos, couple of GIFs of robots doing very specific tasks. But in the next few years, you will see robots working with humans in a variety of settings. So these are some of the figures that I took from certain research groups or certain companies, which are working in space, healthcare, defense, education, and homes. And I'm really positive that we'll see a lot of these robots, but in these domains, helping humans do the task either more efficiently or more safely. And like this is something that a lot of you would be working on to make this possible. So I'm really excited for that. So before we go to the final part of the talk, where we're talking about some of the particular research problems or research questions that are open that we are currently thinking about, I'll stop here to take some questions if you have any.
I have one. So why is it that model specification planning has a high labeling effort again?
Okay, so let me go back to the slide. So here, when we do this interim approach, where there is some amount of model specification and some amount of planning, if we go deeper into it, which we did today, the models that the robot is using could be learned with data, and if they need to be learned with data, they need labels to learn from that data, and this labeling might be this labeling requires some human to provide those labels. And if you are really like extending your robot to do very complicated tasks, to learn these models, you might require large amount of labels, and that's where manual effort is involved.
Mm-hmm. And why would it be limited to small problems? Because of just how many things it would have to, how many labels it would need? Okay.
Exactly. So it is limited to small problems for a couple of reasons currently, and this is something that is being worked on. So it's limited to small problems, first of all, because of the data needs or because of the labels needs. So for very large problems, the models might be very complex and you might need prohibitively large amount of labels. But the other thing that is very challenging for these robots is when they're planning, essentially what they are doing is they are deciding between what are the different alternatives that they have and what is the best alternative to take at a given point of time. So in a larger problem, you might have many alternatives and many alternatives to think about before you make a particular decision. So if we go to this video, here the robot has many choices. So it can choose which ingredient to deliver, it can choose where to deliver that ingredient, and then it can choose when to deliver that ingredient. And all of these choices, when are clubbed together, like the space of decisions that the robot has is very large, even in this simple setting. And to optimize over all of these different choices is very challenging for today's algorithms to do. One way to address this challenging problem is to use reinforcement learning, but then it has its own challenges. So that's why it's the planning-based challenges, which rely on solving an optimization problem, are limited to, relatively speaking, smaller problems than reinforcement learning.
Okay, I see. Thank you. I have another one.
Yeah.
So I think earlier you mentioned that one of the concerns that we have in regards to robotics is we want to be able to understand what the robot is doing.
Yeah.
But as AI gets more advanced, and like we already have things like neural nets where it's very difficult to understand what they do, how are we going to like be able to comprehend even more advanced AI?
That's a great question, and so I have couple of comments on this. So if you so first of all, as AI becomes more complex, it is definitely more challenging to explain what it does. So I completely agree with you on that. But I think it's even more important as AI becomes more complex to explain what it does. Because if you have a system which is complex and you really don't understand what it's going to do, it's very, like, I feel very irresponsible to deploy it in among people without knowing what the system is going to do. Because it may be unsafe, it might lead to bias, it might lead to all sorts of societal or issues from a human standpoint. So as AI becomes more complex, like, even though the explanation problem is difficult, it's important to solve. And how people are solving it, and including students in my group, is we are thinking about using different ideas from how humans learn about other complex systems to explain AI-based systems. So humans have this amazing capability of generalizing, of making hypothesis by observing something. So here, even if I didn't tell you anything about this robot, and even if I didn't have that caption on the top, you would be able to guess briefly what the robot is doing. Like, it may not be completely correct, but you might have multiple guesses of what the robot might do. And by using this sort of capability of humans to guess and make models of what they observe, we can use that capability and provide them certain examples to explain them what they're going to do. So that's sort of one high-level idea that people are exploring right now to explain robot behavior. But that's just one among many. There are many other techniques that are being explored.
Okay, I see. So with generalizing, you get a general sense of what the robot is doing, but if you wanted to do or to know what the robot was doing in like specific steps, like if you wanted to know what it was doing at each node of a neural net,
Yeah.
how would you understand something like that?
Yeah. So again, let's take an example. So you see this robot do something at the start and something at the end. So I only show you start of the GIF and the end of the GIF. Maybe you can interpolate in between to guess what the robot did. Your guess may not be correct, but you can make that guess. And if I show you a few more examples in between, you can improve your interpolation, you can improve your guess. So if you're explaining a very complex system to a human, maybe one idea, and this is just like one solution approach to take, is to give them sufficiently enough informative examples so that they can make a good generalization of the system. So that's sort of one idea that is used. Yeah.
Okay, I see. Thank you.
Yeah. But this is again like one of those problems which is very challenging to solve, and because AI systems are finally becoming like, especially robots that are working with humans are finally becoming complex enough that explanation is becoming very critical. These problems are also very, like, they are being tackled. They are being tackled only in the last few years. So if you ask me this question in a couple of years, maybe there'll be a lot more exciting techniques that I can share with you.
Okay.
Any other question before we proceed? All right. So in the final, thank you again for the questions. And I cannot again catch who is asking the questions, but thank you for those questions. And finally, I'll talk about some of the upcoming challenges and opportunities that we are thinking about when we are thinking about designing these robots. So as we are sort of working on these robots, I particularly focus on the AI aspects of designing these robots. And I assume a lot of you are also interested in the AI aspects of designing robots. But particularly when we are designing these systems, designing these complex systems that have to work with humans, that have to do physical actions and so on, there are a lot of subfields that we borrow from. And in today's talk, we only looked at AI and a little bit of sensing and actuation hardware at a very high level. But if you talk to a researcher working in this area, they would often borrow from a variety of techniques. I list some of them here. So there's definitely AI that we talked about. Then we need to think about different materials and mechanisms, which might be very important to make the robot either safe physically or like more fast, more repeatable, and more accurate. So there's a lot of work in designing different physical mechanisms and materials for robots. Then there is need for embedded systems, that is computers that can help robots to robots process more amount of data, more amount of computation within a short span of time. And this problem is very like challenging for robots, because robots have to make these decisions very quickly. So as we saw in the videos with humans, the robots were the robots had to reason very quickly within a fraction of a second what they should do next, so that they can adapt to humans, so that they can efficiently support humans. And this is something that will be made possible by more improvements and more advancements in embedded systems. So computers that robots can use to make this computation possible. And finally, because robots are working with humans, these robots, we want these robots to work with humans. It's also very important to think about the human factor, to think about the usability of these robots. So even though I do research in AI, I collaborate with researchers in interaction design, cognitive science, psychology, to help me understand how humans think about these systems, what humans might want from these systems to make these robots better human teammates. So going back a little bit deeper, into some of the open challenges, if you look at each of these desired characteristics again, we can borrow from these techniques to borrow from these fields and work more in these fields to solve some of these problems. So we'll talk about a few of these. We already discussed the challenge of making the robots more understandable through the question, but let's look at the other one. So in the robotic systems that I was showing you before, the robots were not as big as the industrial caged robots, but they are still physically very capable. And one way to make them more safe is to make them compliant. So this is a very exciting robot that came out around 3 or 4 years ago, which is compliant. And what here we mean by compliant is if it detects an external force, it will comply to it. So if, let's say, if it collides to a human, it will not hurt the human, but it will sort of become very, it will sort of adapt to the human's impact. So just to show an example of what the robot can do, I'll show this impressive video. And this is made by a company called Franca Amiga. So as soon as it touches the, so I'll play this again. So as soon as it touches the balloon, as soon as it detects that touch, it realizes that it has come into contact with something it shouldn't have come into contact with, and it stops, and it doesn't burst the balloon. So which is really amazing. And this is made possible by better control techniques for this robots, and by sensing force and torques on the robot's arm. So the robot is using additional sensors and additional control techniques to make this possible. And this is a very exciting area for robots that work with humans, because if we can ensure that the robot is safe by its own software, then we'll be more confident in fielding these robots and using techniques like reinforcement learning to which are susceptible to unsafe exploration. Another sort of very exciting research area, which is like very young but growing a lot, is to think about robots from a very different angle. So this is on the right, we can see an example of a soft robot, which has a very different physical mechanism than the robot on the right. So this is a soft robot because it's soft, it has less, it is more safer to work around with. So this is again like a very exciting area of research where people are looking into not only different control and different AI techniques to make the robot safer, but also different like mechanical and mechanical design and materials to make the robot safer and safer to work with. Another very exciting area of research is to make the robots easier to program, is to help to make them program by demonstration. So here, the robot, if you want the robot to do a particular task, instead of programming what the robot should do, if we can show the robot certain examples of how to do that task, and the robot can learn from it, then we can make the robot very easy to program. So this is sort of the high-level idea of programming by demonstration, where instead of writing a program, what you do is you show an example to the robot. And this is again like a very active area of research where a lot of work is going on, where we are looking into how can you give these demonstrations, how can you give examples, and how can you create algorithms which can learn from these examples to teach the robot a particular task. So here, one example might be if you want to teach the robot to pick up something from the shelf, one option is to write a program. The other option is to show the robot a particular example, and then the robot does that task. Here, there's a lot of interesting work in the industry as well, where novel ways of providing these examples have been looked at. So here, different sensors and different user interfaces are being looked at to show the robot how to do a task. And finally, the question that we discussed a little bit into detail about is as these robots work with humans, as these robots work alongside us, it's very important to think about the ethical aspects of it, the safety aspects of it, and think about how they might influence the humans around them. First of all, very importantly, we want these robots, these systems to be safe. So we want to make sure they are like safe. And one way to do that is to make to explain what they are doing so that a human can examine whether they are safe, and also to make sure that they are not biased, they are not limited to a particular set of users. And this is again like very important question to solve, something which researchers have just started working into. And here again, like making the robots easy to understand is a very important piece of the puzzle to solving these problems. So with that, we have looked at two different generations of robots. One from an industrial setting, which are analogous to robots that can, which were analogous to computers that were occupying a whole room, to a generation of robots that can work with and around humans, similar to computers in the 80s. But as similar to how computers have progressed, they have become much more advanced, much more smaller. Robots also have a very long way to go. So I think robots today are at a stage where computers were in the 80s. There's like a lot of different exciting research topics, exciting research problems to be solved. And these are like some of the problems that I can only imagine. And I'm really excited to see like what happens in this area, what some of you would go on to do like research in AI and robotics would make possible. So really looking forward to that, and any questions that you might have. So, thank you.
So with bias in AI, is that primarily determined by the sets of data that you give it?
Yeah, so bias in AI is determined by a couple of, so there are a couple of ways to, a couple of reasons for having a biased AI system. One is the data itself is biased. So let's say if you train it on a particular setting, let's say if I train the robot in my lab, but now I test it in the factory, maybe the data set in the factory is different from the data set in the lab, and that's why there might be a bias. Another reason might be the robot's objective or policy itself is incorrect or exhibits some type of bias. And so again, like understanding of where bias comes from, what sort of different biases are there, is a very active area of research. But these are like a couple of examples of where the bias might come from.
Mm-hmm. Okay, thank you.
Great. So any other questions or comments? Otherwise, I'll hand it over to Ivy. All right, so I'll stop sharing. Thank you again for being being an engaging audience, and for the questions at each section. So I really enjoyed those questions, and I'll stop sharing now. I see a couple of questions in the chat. So does the robot need to be programmed case for case? Yes, that's so in one of the example settings that we saw initially. So let's I'll go back to that. Okay, so in this setting, the robot is if you're handcrafting a policy, if you're handcrafting what the robot needs to do, you program what the robot needs to do for each case. But by using planning or reinforcement learning, you can avoid this requirement. You can use algorithms or like either learning or planning algorithms to make sure that you don't need to do this. Right. So with that, I'll stop sharing. Ivy, what's the next step?
Basically, like if you're done presenting, if anyone has any questions, they can ask those questions. If there's no questions, I guess we can be done.
Right.
So just if no one has questions, then I guess then thank you for giving the talk today. I'm pretty sure everyone learned a lot. I did too. So thank you.
All right. Thank you again, everyone. And I'm glad that I'm glad that I was able to share this with you. If you have any more questions, and if you do research in robotics or go on to do like more work in robotics and AI, definitely let me know, and I'll be excited to learn about that.
I have one additional question. So
yeah, go ahead.
If we use like machine learning and reinforcement learning, what is the primary way that we kind of transfer their thinking, or like once you have trained the robot, how do you like transfer the trained robotic brain, so to speak, to like other robots?
Oh, that's a great question. So there are a couple of ways to do that, or a couple of sort of solutions to do that, or ideas to do that. So one is, if you can, so in the block diagram for Ross that we saw, there are different modules that a robot might have. So it might have a module for localization and planning. And if you can abstract your problem to certain inputs and outputs, then you can use that module in each robot. So each robot that needs to go from A to B might want to use the same, might need the same planning capabilities. And if you can define the inputs and outputs in a way such that it can be used across different robots, you can do that. So one way to do that is through the reuse of algorithms, such that making the system modular and reusing algorithms. That's sort of one software-based, like a software-specific way to do that. Another way is to like use an idea called transfer learning, where you use some small amount of data from the new domain where you want to transfer your learned policy to, or learned robot to. So let's say if I trained a robot in my lab with a lot of data, and then I need to move it to a factory, then there are techniques called, there is a research area called transfer learning, which looks at, if you have some small amount of data in this new domain, how can you transfer the data that you have collected in your original domain to the robot that you've trained in your original domain to the new domain.
Okay, I see. Okay, thank you.
Yeah. So if you want to like learn more about it, the question would be, the search item would be transfer learning. Yeah.
Okay.
So I see Yo-Yo raising a hand. Is that a raised hand?
Yeah, sorry, I have a question.
Yeah, go ahead.
This is kind of random, but do you think robots will take over the world soon?
Oh no, that's a good random question to ask. So it's so my answer is definitely not. So I think robots are limited in what they do today. So they are like, they do what we program them to do, and because of that, I see this question, or like I see this question, and like maybe sometimes in science fiction novels, or in sometimes in popular news. But this is something that like from my standpoint, like having worked with robots a lot, I don't think so this is a immediate worry. I think what is more important to think about, what is more important to like pay attention to, is the slides that we saw in the end, where even though robots might not, the robots don't have any capability to take over the world, but they have this potential to cause like unintended consequences. So let's say if we overtrust an autonomous vehicle, we might not pay attention to it when we need to. Or if an algorithm is biased, it might lead to certain certain side effects that we might not want. So those are the immediate challenges that robots and AI systems present that we need to pay more attention to. And that's some of the things that I think about, and see how we can make systems so that they don't fall into that trap, or they don't have those limitations. Thanks for that question. And it is like it's a good question to think about, and it's a good question to know why it's not. It's good to know why it's something not to worry about. Yeah.
So if we have further questions or something to talk about in regards to AI or something like that, are we free to contact you using email?
Yeah. I'm happy to respond. I'm best available on my work email. So that's I'll share my screen again quickly. So that would be this.
Okay, thank you.